So let me try to, since I was asked during the break, so let me try to kind of rephrase basically repeat the logic again, since some of you might have probably lost just now. That what are the S and all that, etc. What exactly was I doing? So basically S just now, you should really think about it. As a kind of higher dimensional. So just now, I gave a very simple one degree of freedom example.
Sorry, the microphone is off.
Microphone's off, yes. Thank you. Okay, better. Okay, so just now I gave a one-dimensional example that where the conserved quantity become important. Then, okay, then I move on to say, well, okay, eventually I have a integral that if I substitute away, because E is fixed, so I can write P as the function of E and the NQ. Okay, so then I obtain something like this, right? So basically the S function here, which I define be something like this, is precisely a high dimensional analog of this statement. So E here are precisely, well, so here you can actually view this expression as a function of both not only Q, but also this constant E. Okay? So here, again, now if you have many degree of freedoms, then you can have many conserved quantities. And basically you can, but however, once you know certain set of quantities are actually conserved, then you can do the same kind of substitution, then substitute away your momentum, then to rewrite the expression as such. But what makes the general case more complicated is that, so in this one-dimensional problem, there's no issue of path independence. When you're defining the integral, it's really just a one line. You are actually doing the integration. But for general higher dimension, you do have to worry about if this thing is actually well defined. Okay? So that's why we want to show that there's actually a path independence, or basically showing a higher dimensional analog of a Stokes theorem. And that can be ensured basically by this condition, okay? And this condition basically can be implied by the fact that the various quantity you are setting Fi equal to constant from actually Poisson commute with each other. Okay, so that was the line of the that was kind of the line of logic that I was trying to express towards the last 10 minutes of the lecture. Okay, so hopefully the notes will be on the web. So hopefully when you run through it again, that will become more clear. Okay, so now I would like to basically talk about, well, so how do you actually generate those various kind of conserved charges? So, but before I get into that, actually let me just talk about something which will be quite important. some of you may encounter before. That is, so basically improving the path independence, or basically the d alpha equal to omega f equal to 0, we are assuming that we are deforming the path like continuously. This is basically like for those of you done my complex, done my applied math 3, they know what I'm getting at. So that they are actually deforming continuously. So that's why you can do that. You can just shrink the contour integral, well, basically contour integration to a point, no problem. Contour vanishes. Yeah. But however, if now in your phase space, or basically on this, or even on this manifold NF, they are non-contractible cycles, which generally are the case. In fact, that even in the one-dimensional example we are thinking about, this is a non-contractible cycle. Once you have an energy greater than 0, it's a finite radius, you can't shrink it. That's that. And in fact, I'm not going to try to prove this, but so in general, I could say that in general, the surface MF has non-trivial cycles. And in fact, actually you can even think about the simplest case that, so just now I was talking about, so actually this is really for simple harmonic oscillator. So for potential Q squared, but you can consider that you have a system of n simple harmonic oscillators, which feels like this, but they don't talk to each other, so you just sum over all of them. So that's your Hamiltonian, okay? But you basically have n conserved quantity, each one is given by, in fact, you can have different frequencies, like this. So now you are having a system of n degree of freedom. Okay. And if you look at a surface where all this HI to be constant, then basically what you have is now you have basically in your 2n dimensional phase space, you basically have n non-contractible cycles, which is given by something like this. So you have one here, and unfortunately I can't draw 4-dimensional space here, but you can imagine that there are basically n different cycles. Like, well, simplest case, you've got 2 S1 and S1, for those of you who don't know. You basically have a torus. Okay? So what's really happening here that for this n harmonic oscillator, then the surface where the h I equal to a constant is basically an n-dimensional torus, which is basically a direct product of n cycles. Okay? So, and know all of those, if E are finite, then they are not really contractible. Okay? So it's actually very generic. There's nothing really exotic about it. So, and generally, and this is some statement I hope you can I guess you will have to take a leap of faith here. That so generally, in fact, so just now we're talking about simple harmonic oscillator, but generally for other dynamical systems, it's constant. Basically, the surface where the conserved quantity are basically constant. Well, when you fix it on constant, then it also has a non-trivial contractible cycles. And actually, if you integrate. So basically now the generating function we talk about. So as generating function. So when you integrate along those non-contractible cycles, instead of being instead of vanishing, but rather it actually picks out non-trivial contribution. So a certain given cycle, so I should really draw something like so there are different cycles that we can integrate our doing. Basically, you can imagine just that we can do a line integral along different cycle here. But now, for those non-contractible cycles, that you actually have a non-trivial contribution towards your generative function along those cycles. Or if you want another way to put it, is that those generating functions actually become a multi-value function along basically on this MF in the phase space. And those guys you're actually familiar with. I mean, so what are those non-trivial contributions? Well, so those guys are precisely the famous action variables, which some of you may encounter at the, I don't know, undergraduate mechanics course, which is basically given by so here's J here are labeling precisely different cycles, different non-contractible cycles that along your MF. So for those of you who did the math, that you should really think about this is as a Riemann surface, and you are actually integrating over with a different A cycle and B cycles. And so if you want the Y type encoding, the P, D, Q, J here are really the kind of meromorphic one formed on your Riemann surface. So now, if we can consider a canonical transformation into, basically from, so again, this is actually, this capital I here are again function of P and Qs. And in fact, that there exists a canonical transformation yeah, okay, sorry. So let me just make one more statement that yes? The capital I? Is an action variables. So actually what difference from the S just now was that S, I was just saying, well, okay, we integrate over some two arbitrary points. Okay, just now we were defining the generating function between Q0 and Q. Okay, and when we were proving that S actually exists and well defined, we were saying, well, okay, so if there's a non-contractible cycle, sorry, there's a every cycle is contractible, then this thing should be independent of the path, and therefore this thing vanishes. But generally, just like we learned in the complex analysis, that if on the surface with a non-contractible cycles or basic singularities, like we know, right? Oh, okay. And if we integrate, if you're doing the same integration along those cycles, and that's defines our action variable I.
It's something like winding number.
Yes, something like a winding number, precisely. It's one of the, that's one of the conserved quantity as well. Okay, and you know this is actually, so of course this is closely related to the conserved quantity F we were defining, right? Because this is actually defining on the surface MF, right? So P here, as I was trying to write down here, is that it's a function of Fi and Qi. Okay, but now you integrate over all the Q dependence. So now it becomes just a function of basic conserved quantity in your time evolution. Okay? Yes?
I have a question. Is this formula has relative with the corresponding theorem? Because this is just the integral over the.
Let's see. Maybe on top of my head, I can't work it out. So okay. So sorry. So again, this is a function of those conserved quantity F. So we can imagine that there's another canonical transformation. So basically, again, we can construct a generating function that now in terms of the action variable, which if you want, they are basically almost the same role as F, but you are just changing a different basis. So we can, again, define a generating function which involves I and your original position coordinate Q, and in such a way that the momentum is given by ds qk, and there's a dual variable to the ik, which actually becomes the famous angle variable. And why this is called angle variable, it becomes very clear momentarily, because this angle theta has a nice property that if you integrate along the various cycles on your MF, is precisely given by the delta function. And we can show this very easily, almost by definition. So basically, theta now actually plays the role of angular coordinate along each of the non-contractible cycles. So to show this, we see that, well, so this guy is basically equal to dik this way, I guess. Cj dx, by definition over here, and this is equal to, just expand it out, so is that differential? That's the definition of ds. So, but on the surface MF, we know this guy is 0 because di vanishes. Since I is a function of f is constant, therefore I is constant. So, and from this we can deduce that this guy is equal to dqi just by substituting this expression into here. Okay? So, and this is nothing but 2 pi ik over ij, which is delta ij. As requested. So it's actually also trivially to show now that once you realize I are precisely a function of f, they also cross on commute. So, and we can also write down the time evolution equation for them, and the one for I is simple, it's simply 0, which you can again show very easily. And theta is given by dh dik. So h here now should really be expressed as a function of I and theta. Okay. So this again is constant. And we deduce that theta k is basically. So if you want, you can basically view the action variable and the angle variable as kind of like preferred canonical transformation on your constant energy surface that basically specify the cycle you are integrating over basically your basically you're doing your line integral over. What I really want to say is that you actually choose a basis for your meromorphic one form. So, but I think that might as well be speaking German or something. So, so those guys, so basically action variable and the angle variable play a quite important role in our subsequent discussion on integrable system. Okay, so I'll give an explicit example of what those guys are. So far I've been stressing that the importance of those commuting conserved charges in a dynamical system and establish an integrable system and so on. So now, then the next question you should be asking is that whether there can be a systematic way to construct those different conserved charges. And it turns out they are. I mean, they are a systematic way to do so, even though with some difficulties. But when those methods actually exist and when those methods actually works, it actually becomes a very powerful mechanism. So, and you will see why, basically now. So, and this systematic way of constructing a set of commuting conserved charges when you are given a integrable or a dynamical system in general is something called a lax pair. Okay, so basically lax pair is very simple. It consists of a set of matrices. So lax pair is really a set of matrices, usually in the literature denoted as L and M. So matrix value functions of your original canonical variables, Q, I, PIs. And basically, they obey a set of equation or matrix equation, which goes like, if you look at it, so basically all the entries, if you want, all the entries are really L11, but each of them are functions of P and Q, so on. And the same goes for N. Okay, so, and they obey a set of simple equations. Is that when you look at the time evolution of the matrix L, is simply given by the commutator. Oops, no, not H, not of M. The matrix M with L itself. And this is, of course, is a usual matrix multiplication. For those of you familiar with. And the point is that this set of simple equation or matrix value equation, when you write down its various components, it's actually equivalent to our original Hamiltonian equation of motion. Yes?
L and M arbitrary functions.
No, they are very specific, nice functions. You have to find them.
So some two specific functions, so and then satisfies this different.
Right. And in such a way that, no, also important is that they are equivalent when you write down various components, right? So M and L, as I was writing out just now, they are L11, P, Q, and all the entries are functions. So are the N's. Okay. And when you write, you can of course do a time derivative. You can multiply them together and so on, right? But the point is that when you write it out, then they have to be equivalent to your various Hamiltonian equation of motion.
So this is Dirac bracket, but
This is not a Dirac bracket. It has nothing to do with. Okay, fine. Eventually, Dirac bracket, quantum mechanics and matrix formulation.
yes.
But this is just a classical system right now.
My question is, how do you derive this equation?
Well, generally, that's what I'm trying to say.